Hello, physics fam. We're going over free body diagrams right now. Let's just walk through all the ones from our homework to see how we're doing and at least get a start on getting used to all the different types of forces and how we should draw them. So number one is a physics book, just rest upon the table. So we know that anything on Earth is going to have the force of gravity, and since it's sitting on a table and it's not accelerating, that the normal force should equal it out. If you look at letter B, it says a skydiver falling has reached terminal velocity. Well, if you're a skydiver, we know that there's definitely a force of gravity. And since you're reaching terminal velocity, that means that you have no acceleration. What it really means is that the air resistance pushing back up on your body is going to be equal to the force of gravity pulling you down. And we're going to look at that when we talk about skydiving a little bit more. How about letter C? A large crate is being pushed leftward at a constant velocity. So we have it being pushed to the left, so that means that would be the applied force. But since it's moving at a constant velocity, that means there can be no overall net force. So that means even though you're pushing it to the left, there must be a force opposing it to the right. That would be the force of friction. But since this object is still on the ground and you're pushing it, don't forget, there is still a force of gravity, and since it's touching a surface, there's still the normal or support force. If we look at letter D, a sledder has reached the bottom of the hill and it's coasting rightward while slowing down. All right, so this object is going to the right. That means that friction would be opposing it. So the force of friction would be there. You would still have your force of gravity, right? That's your Fg. And then you'd still have your normal force pushing up. Since you are coasting to the right and there's no applied force making you go forward, it's just your inertia that's pushing you forward. Really only the force of friction is acting in the horizontal direction. How about a ball that is moving upwards towards its peak and we're not caring about air resistance in any way? So this is just the force of gravity acting on the object. There would be really no other forces acting on it because it's up in the air. And again, we're ignoring air resistance. So it's really just the force of gravity pushing it down. How about letter F? An air track glider moves rightward at a constant speed. I know you're not familiar with an air track glider. To be honest, I'm not really that much either, but it's supposed to be a frictionless surface that an object can slide across. So if that's the case, let's see. You would have the force of gravity pushing down, and air would be pushing back up on it, so there'd be some type of normal force. But technically, there'd be no force of friction, or just basically inertia is allowing the object to flow from one side to the other. That's kind of an oddball one, though, because we're not quite used to that. But you get the idea, at least if there's no friction, there'd be no horizontal forces, just up and down forces. All right, if we move on to G, the brakes are applied to a rightward moving car as it skids to a stop. Well, if it's a car, it's on the ground, so there's a force of gravity, and there's definitely a normal force. And since it's moving to the right and skidding to a stop, that must mean that there is a force of friction opposing that motion. But otherwise, there's no applied force that is trying to push the car forward. So therefore, the only horizontal force is the force of friction. For letter H, a spider is slowly descending a thin silk thread at a constant speed. So obviously the force of gravity is pulling down on the spider, and there is some type of force of tension because you have the spider web that the spider is dangling from. You want these two arrows to be equal in size because if you are at a constant speed, that means that you would have no acceleration. So therefore, the magnitude of the two forces should be equal so that you're in equilibrium. Consider that. For letter I, the projectile is moving upwards and rightwards towards the peak of its trajectory. So if we ignore air resistance on this one, all right, this object is just flying through the air because of inertia. So the only force really acting on it after it's been launched is the force of gravity. If we wanted to get into the air resistance and all that, it would definitely be opposing the motion. But for simplicity's sake, let's just say we're ignoring air resistance on that one. If you drew that on there, I totally understand why you did. It should be more explicit whether or not we should include air resistance or not. Looking at J, an elevator is rising at a constant velocity and it is not touching the elevator shaft. So, if the elevator is rising, there's a force of tension or some type of cable pulling it up. But we know that there's weight or force of gravity pulling it down. But since you're rising at a constant velocity, we know that that means that there is no acceleration. And therefore, these two forces have to be in equilibrium. Otherwise, Newton's second law states if there's a net force, you must be accelerating. For this next one, interesting enough, you have an upward rising elevator, but it's slowing down. So if you have an upward rising elevator, that means your velocity is up. But if you're slowing down, you're decelerating. So acceleration must be down. So that must mean that your overall net force must be in the downward direction, which means of these two forces, the upward force of tension, gravity must be a bigger force in this time and case because you have to have the acceleration and net force be in the downward direction. There's no left and right forces because it's not touching the side of the shaft, so therefore there's no friction there. And last but not least, you have a force applied to accelerate a crate. So this thing's going to accelerate. I'm just going to choose arbitrarily to have it accelerate to the right, which means that my net force overall has to be to the right. So in this case, we are going to have an applied force pushing it to the right, which means my force of friction should be smaller. Okay? And don't forget, if it's on the ground still, I have normal force and force of gravity. But in this case, if it's accelerating to the right, your net force should be overall to the right, which means your applied force should be larger than your force of friction. All right, this is just the beginning of free body diagrams, but hopefully this helped you out a little bit to walk you through some of the things you're going to be expected to do. Take care, physics fam.